So in this lecture, we will discuss about the amplifier design. So what is an amplifier? An amplifier is a electronic circuit that amplifies the signal. For example, if I have y equal to ax, so this is an amplifier if a is greater than 1. So we want to amplify some weak signal. So this is what we are going to learn in this lecture, and we will use the BJT to design an amplifier. So in the previous lecture, this is what we have seen, that this VVE voltage will generate this DC current IB, okay? And if a small signal VVE is added in series with this VVE, this will result in an additional small signal current IB, and of course it will result in a small signal current IC here, okay? So, and of course this small signal IC is beta times IB, and because this beta is, we know that it can be 50 to 350 or even more, so that is an amplification, basically amplification of the current, you can say. So now what we want to do is we want to do a voltage amplification, okay? Okay, so because of this small signal applied, I'm getting this IB, and of course this I'm getting an IC, which is beta times IB. Now if I want to convert this current into voltage, I can do it by passing this one through a resistor. But before that, what I will do is I'll fix this collector at a potential which is VDD, or which is basically the supply voltage, okay? So I'll fix this at some voltage, okay? And then I will use a resistor to pass this current, okay? To pass this current through this one. So the IC current will be passing through this one. So what we will see is that the current will get converted into voltage at this collector. So let's call this node as V out, okay? This is both the AC and the DC component, okay? And if we write down the expression of the V out, it is going to become something like this: VDD, the supply, minus IC into R, IC into RC. Let's call this resistor to be RC because it is connected to the collector. So basically what I'm doing here is that I'm converting the current, change in the current, into change in the voltage, because finally in an amplifier I want to feed input as a voltage and I want to get output as a voltage, okay? So basically the voltage amplification, okay? Of course there are also current amplifiers, this we will see later on. And here when I'm writing this VDD minus ICRC, this C is small c, basically this IC is basically the summation of this DC IC and a small change, okay? So now I can write this one as VDD minus beta times IB RC, okay? So this is basically the change. So this is basically this one, okay? DC plus the change in the IB current, okay? So now what I want to know is how does this V out change with the change in the VVE? So I need to do that by doing a differentiation. So I can get the change by just doing a simple differentiation, okay? So therefore my dV out by dVE, so this VE is basically this voltage VVE, okay? So change in this V out by change in this overall voltage, basically this one only, okay? So is equal to So now if I differentiate this V out with respect to VBE, this VDD is constant. Okay, we are using a constant supply voltage. Okay, so this will become 0 minus, I have beta RC, which is basically constant, and DIB by DBE. Okay, okay. So now, so implies my dB out by dBVE is equal to minus beta RC dIB dBVE. Okay, so basically what I'm doing here is the differentiation of this IB with respect to VBE. So this is the characteristics curves of the IB versus VBE as discussed in the last lecture. So let's copy this figure. Okay, so here basically what we are trying to do is, here we are differentiating this DIB with respect to VBE. Basically we are trying to find out the slope, and we know this is this expression is nothing but the slope. So what I can do is this will be the slope at a point my IB is equal to IB, and at this point the slope is equal to 1 by r pi. So the whole expression is implies, so dV out, basically the change in the V out, I can write it as this, like this, and this is as the VBE, the change in the total overall voltage VBE is equal to minus beta RC, and this whole thing is the slope at 1 by r pi. Okay, and r pi we know that it is VT by IB. Okay, so what I can write it here is that minus beta RC so beta IB is, we know that it is IC RC by VT. Okay, so this is the gain, this is the voltage gain. Okay, for a small change, if I am applying this signal here, the change in the output is given by this IC RC by VT. Okay, and of course we can make this as the input voltage V in. Okay, so if I make this change in the VBE as my input signal V in, then the gain of the amplifier V out by V in is definitely the gain of the amplifier. It is the voltage gain. Sometimes it is represented by A amplification of the voltage V is equal to minus IC RC. Of course, this is the DCIC. Okay, by VT. Okay, and of course by selecting a suitable value of ICRC, we can get a gain which is even more than 100, and VT is at room temperature, it is 26 millivolt. Okay, so this is the basic operating principle of a amplifier. Okay, so this is basically a amplifier which is also called as the common emitter amplifier. Okay, so why it's called common emitter, we'll see that. Okay, so let's redraw this circuit again. So this is a common emitter amplifier. Again, the same diagram which we had drawn previously is the same one, except change in the VBA I have written as V in. So input is applied at a base and the output is collected from the collector. And of course, when we are seeing this change in the input, we are seeing it with respect to this ground. Okay, and of course the output also we are seeing with respect to this ground, and because the emitter is grounded, that's why this is called common emitter. Okay, if you see this transistor, as we know that it's a 3-terminal device. Okay, so I have my base, I have my collector, I have my emitter. Okay, and if you see amplifier has input and the output. Okay, so in this case we have applied the input here and observed the output here. Okay, this kind of configuration is called common emitter, because we are not using this emitter, it is grounded. Okay, so if I am applying the signal at the base and grounding it, okay, basically AC grounding it, and then see the output at the emitter, this kind of, you know, configuration is called common collector. Okay, so because I have three terminals, one can be common, means one can be grounded, and that one can be, you know, we can provide input one and the CD output at the other. Okay, the other type of configuration where we'll be grounding this, you know, base and providing the input at the emitter and then seeing the output at the collector, this kind of configuration is called common base, because I am grounding the base this time. Okay, so we will see three kinds of configurations. Of course, there are multiple options. I can provide input at the collector and see the output at the emitter as well, but those configurations are not very useful. Only usefuls are I'm providing the input at the base and seeing at the output. I'm providing input at the base and seeing output at the emitter, and I'm providing input at the emitter and seeing the output at the collector. Okay, so first we will discuss the common emitter amplifier, and eventually once we know how this operates, the basic principle, understanding common emitter and common collector will not be difficult. So as discussed previously in the previous discussion, we know that the gain of this amplifier AB is basically V out by V in, and it is equal to minus ICRC by VT. Okay, of course, we don't have to remember this formula. We just need to understand how it works, and we can always derive this. And the important thing here is that this negative term, okay, this negative term indicates that there is a change in the phase from the base to the collector. That means if I'm applying a sine wave, something like this, I can see a 180-degree change in the phase. Okay, so which is very obvious here, because if I am increasing this, you know, current IB, okay, this IC current will increase, and there will be increase in the voltage drop. That means this drop voltage is going to drop, okay, because of the increase in the IR drop, like ICRC drop, right? So that's why they have this opposite phase, right? But what is important is the phase shift, 180-degree phase shift. That is fine, that's not an issue in an amplification. What is more important is the magnitude. So these negative terms is just, it will just shift the phase by 180-degree, but everything, the magnitude is the most important factor. Okay, so now let's try to derive this same expression of the gain by using the small signal model analysis. So let's try to draw the small signal of this common emitter amplifier. So let's try to draw the small signal circuit of this transistor first. So I have basically this is my R pi, okay. IC equal to beta times IB, okay. So this is my emitter, this is my base, and this is my collector. So I have just drawn the small signal circuit that we have derived in the previous discussion. So basically this one, I have just redrawn this portion, okay. So this represents my this BJT, okay. So now if you see here, the emitter is connected to the ground, okay, and the input B in is applied to the base, and because this is a DC voltage, and we know that in a small signal analysis, as we have discussed before, all the DC source should be shorted, okay. So that means my V in is connected to the base, and this should be grounded. Okay. Similarly, this RC is connected to the collector and the other end is connected to VDD. Again, this should be shorted. That means the other end of the RC will be connected to the ground, something like this. And this RC should be connected to the C. Okay. So when we say that the for the AC this signal is grounded, it means that in reality it is not grounded. In reality, this is not ground. In reality, it is VDD. But for the AC means for the change, right? This is like a zero, because there is no change for the zero. So it is like for the AC signal for the AC, right? There is no change here, so it is like a ground. And this consideration that this is a for AC ground, this makes the analysis very simple. Okay. And of course we are observing the output at the collector, so this is my V out. Okay. Okay, so now here we can try to find out, we can try to do the simple network analysis and try to find out the relationship between V out and V in. I am supposed to get this kind of expression for this as well. So if you see here, this IC current is flowing through this, right? And this small current is flowing through this because of this V in, and it is developing this voltage VBE. Okay. So now, because the current is flowing from ground to here, this IC current, so my V out will be equal to, IC minus IC into RC. Okay. So therefore my V out is going to become minus IC into RC, because it is going from this ground, it has to go to the negative potential, otherwise the current will not flow. Okay. So because I'm considered the current direction to be in this direction. Okay, in this direction. Okay, and now what is my IC? It is equal to minus beta times IV into RC. Okay, so this one. And what is IB? IB is basically R pi, BBE by R pi. Okay, and in this case, because this node is grounded, so BBE is equal to V in. Okay, so I can write it as minus beta RC B in by R pi. Okay, so therefore my gain AV is equal to V out by V in is equal to minus beta RC. We know that R pi is again IB by VT, which is equal to minus IC RC by VT. Okay, so if you see here, we are getting the same value of the expression, even though we have used this small signal analysis. So if we have small signal analysis correctly, I'm supposed to get the same expression of the gain if you go by the method of the differentiation. Okay, so one way is that you can find the expression of this V out and do the differentiation with respect to the V in, and I can get the gain. Okay, or the other way is we can use the small signal analysis, which is basically has come from the differentiation only, because we know that this R pi is nothing but a differentiation. Okay, and of course we need to short all the DCs. And here also, if you see, the differentiation is making these constant voltages ground. Okay, so either way is fine, but this small signal analysis becomes very handy, and especially if I have to solve a very big complex circuit, this becomes very useful. Okay, if I'm going by the method of the differentiation, what will happen is that I'll have to write a a lot of equations, and differentiation may be very difficult, or it may be time consuming. Okay, so we will be using this approach of small signal analysis, to find the gain of any amplifier. So now if you observe this amplifier, we have two DC voltages. One is the VBE and other is the VDD. Okay, and this VDD, we know that this can come from the battery. It can be 5 volt, it can be 10 volt. But then what about the VBE? Okay, so whenever we are purchasing an electronic device, we have only one supply voltage. If I am a manufacturer, and if I tell that for my product I need to use different batteries, right? I need to have a 0.7 battery, I need to have a 10 volt battery, 3 volt battery. So my product will not be sold. Okay, um, so generally in every product there will be only one supply. So we need to generate this VBE voltage from this supply itself. Okay, we need to generate multiple voltages from one single supply. So let's see how do we generate this VBE. Okay, so we know that the basic principle that uh, you see here, what I need to set is I need to set this IB, DC voltage IB. Okay, so this is what this DC voltage is doing. And we know that in a diode, in a PN junction diode, if I have a diode, and if I want to set the current which is flowing through a diode, right? So we know that this is defined by the resistor R. Okay, so VDD, right? If so we will use the same technique to bias, right, to fix this IB. Okay, and of course then we will see how to apply this input signal. Okay, so this type of uh, fixing this DC voltages is called biasing. Okay, so this is called biasing. So let's see how to do that. So the technique that we'll learn is the self-biasing technique. So this is the self-biasing technique of the CE amplifier. CE means the common emitter. So it is also sometimes called as the CE amplifier. Common emitter amplifier. Okay. So in the self-biasing technique, basically what we are doing is we'll be using one resistance here. So resistance RB. Okay. So this resistance RB will decide my current IB. So we know that the drop, right? The drop in a PN junction is equal to almost 0.7. So because this is a forward bias PN junction, and I was also mentioning before that we need to treat as if it's like a constant drop model, right? So the same analysis that we used for the diode can be used for this BBE. Okay, so basically what it means is that the expression of this IB here is VDD minus this one, the VBE on, which is basically 0.7 by this resistance RB is equal to IB. So what I have done is this IB resistance is the potential difference across these two nodes, and which is basically this VDD minus this is VBE on. Okay, so the on voltage, we know that this is around 0.7. Okay, so considering that, then implies my IB becomes VDD minus 0.7 by IB. So by this we can set this current IB. Okay, so this is the equation that we will be following for this. Okay, and now the next question is, how do I apply the signal V in here? We know that we are observing the V out here, and how do I apply the signal V in? So to apply the signal, we will be using a capacitor. Okay, and we will be feeding the input signal V in through a capacitor. Okay, so basically what is happening is this capacitor will be blocking the DC. if I'm connecting this V in, it will not affect my DC biasing point, DC analysis, like whatever we have done, it's not going to affect. But what is happening is, because this capacitor, it's past the AC, so whatever the input signal V in I'm applying here, it will directly be appeared on the other end of the capacitor. Okay, so it is blocking the DC. If there is any DC thing is here, it will be blocking it. Okay, so if instead of connecting this capacitor, if I would have connected this one directly, then it would have been disturbed this biasing point. Okay, because I'm trying to connect this close to the ground, so voltage drop across this VBE would have been 0 and this current would have been disturbed. Okay, so that's why we need to use a capacitor to just allow only the AC to pass. But then the question comes is, what value of capacitor I should select? So you know that the impedance of the capacitor is given by 1 by J omega C. Okay, CC is the coupling capacitor. Basically it is coupling the AC. Okay, so that's why it's called decoupling capacitor. So I need to make sure that this whole impedance is very small. It's close to 0. So for a particular value of the signal omega, right, if particular frequency that I'm going to amplify, then I need to select this value of CC such that it is like almost short, right? It almost short at the frequency, desired frequency that we want to amplify. So the conclusion here is that this amplifier cannot amplify the DC voltages. Okay, it can amplify only the AC signals, right? Change in signals, so it cannot amplify the DC signals. We will discuss about this one more in details in the future classes, but here what important thing that we need to learn is that the whatever the input that I am applying here, the AC signal is getting directly coupled here and it's getting amplified. So now let's try to draw the small signal model of this one and try to estimate what is the gain. Okay, again let's repeat the same thing. So for the transistor, we know that it is, I have my R pi and I have a current dependent current source, which is IC equal to beta times IB, and of course my RC is connected here and the other end is grounded. Okay, and I'm observing V out here. Okay, again in this case also the emitter is grounded, and if you see here, now my this RB is connected to the base and the other end will definitely be grounded because it's connected to this VDD, so which is AC wise it is ground. So my RB is connected to the base and the other end is grounded, and of course I am applying this input signal V in here and the base. Okay, okay, so here if you see the capacitor should come here, right? Capacitor is supposed to come here, something like this. But again, for the AC, as I was mentioning, this whatever signal that we're applying, it will directly come here. So AC wise, this is almost like a short because the 1 by omega C is almost close to 0. So we can treat as if it is a short. Okay, or even though resistance is there, but it is very small and negligible. Okay, so now we can analyze this circuit. So here the analysis is very simple because this V in is directly coming across this VBE. Okay, so that means this V in is equal to VBE. Of course, because of the V in, maybe some small signal current will flow through this resistance, but that is fine. But it is directly appearing across this VBE. Therefore, the gain is same as whatever the previously that we have derived, that the AV gain is equal to minus ICRC by VT. V in is directly appearing across this VBE. If I would have some resistance here, the source resistance of this source RS, of course then the expression would have been different. This we will see later. Okay, So when we will discuss about the next type of biasing technique, we will introduce this RS and C. So now we will see a resistive divider biasing technique. Okay, so in the resistive divider biasing technique, instead of just biasing with a one resistor, I'll have one more resistor here. So RB2, okay. So this is called the resistive divider biasing, okay. So note that in this technique, the analysis becomes little bit changed, okay. Okay, so how do we solve this problem? So here I have my current IB, and I have this current, IRB1, and the other current which is flowing IRB2, okay. And of course we know that this current is split, okay. So this is one side is going as IB and one side is going this side. So we can solve this whole network by using simple KCL and KVL, okay. But we will not be doing so, okay. The reason is, of course, for this case it is fine, but when the circuit becomes more complex, so we will so more complex it becomes difficult. So we will be going by the Thevenin's theorem. So we will apply Thevenin's theorem here, okay. So to do that, let's copy this whole thing again. Okay, so how will we apply the Thevenin's theorem? So of course, when we are doing the DC analysis, we are assuming that the V in is 0. There is no V in. Okay, so that means this is shorted, and of course, then of course we know that because the capacitor blocks the DC, so we can of course remove this portion as well. Okay, so yeah, so now if you see here, the VDD is connected here and here, okay. So what I will do is I'll just split this one, okay, and connect my VDD this side. So it's the same thing, either I short it and use a single supply, or just splitting for simplicity, okay. And now if you see here, I can just, remove this line. So I'm breaking this connection, okay. So here what we are going to do is we are going to find out the Thevenin's equivalent voltage and the resistance of this whole portion, okay. So if you see here, this is like a load, okay. This is like a load for this whole network, okay. And we can find out the Thevenin's equivalent voltage and the resistance at this point, okay. Okay, so basically what we do is we'll find out the Thevenin's equivalent voltage and the resistance at this point, okay. So the Thevenin equivalent voltage at this point, VTH, okay, and of course the RTH. So the this is my RTH, okay. So the Thevenin's equivalent voltage at this node, VTH, will be given by the current flowing through this one, okay, will be basically VDD by the summation of this resistance, which is RB1 plus RB2, okay, and the voltage at this node will be multiplication of this current I and this RB2, okay. So this is my Thevenin's equivalent voltage at this node when the load is not connected. And to find the Thevenin's equivalent resistance, we know that we need to short all the voltage sources, and if there is any current source, we need to open it, okay. So yeah, so the equivalent resistance you see here, this is grounded. Once this is shorted, this is ground, this other node is also ground. So basically RB1 is parallel to RB2, so my RTH so my RTH is RB1 parallel RB2, okay. So let's try to draw the whole thing again. So I have my VTH here. and we have this resistance RTH, okay, and of course I have this network. The emitter is connected to ground, and okay, so this is the equivalent circuit of this whole thing, okay, where my VTH is given by this expression and RTH is given by this expression, okay. So this way I can easily find out my current IB. So the expression of this IB will become very simple now. So my IB will be given by the VTH minus this BBE on voltage. So this is my base, this is my emitter, and this is my collector, okay. So VBE, the on voltage, this is, we know that it is 0.7 by this RTH. So using the simple expression, we can find out this current IB, okay. So the next thing is, how will the small signal model of this one look like, okay. So if you see the small signal model, if you see here, these RB1 and RB2 is connected both to the base, and for small signal model we need to ground it, okay. So once I ground it, and if you see at this point, this RB1 and RB2 are parallel, okay. So the small signal model will be similar to the previous one, except instead of RB, I'll have RB1 parallel RB2. Okay, and as in the previous case, this resistance was not affecting the whole gain. Okay, so in this case also it will not affect the whole gain until and unless I have a source resistance. Okay, so if I have a source resistance Rs, then there will be a voltage division, and this resistance will come into picture when we are trying to calculate the gain. So of course this is important. We till now we have been considering a source without resistance, but in the real life case, any source that we are considering, any sensor like the microphone. Now I am speaking on a microphone, and the voice is getting recorded. So it also has a resistance. So any sensor or any voltage source that we see, any signal that we want to amplify will have a resistance in series Rs. Okay, and once this Rs comes, then what will happen is so this whole resistance will come into picture when I am trying to write the gain expression. So to see the effect of Rs, let's try to solve a problem by considering the actual values of RB1, RB2, RC, and the beta of the transistor for a given VDD and for a given Rs. So this is my example problem. So here given the beta of this transistor is given to be 295. Okay, so let's consider the value of RB1 to be 186 kilo ohms, RB2 to be 15 kilo ohms, okay, and RC to be 3 kilo ohms, and this Rs 2 kilo ohms. And of course the CC we have considered such that, you know, for the AC, the frequency of which we are amplifying, it's almost like a short. The first thing that we'll be doing is we'll do the DC analysis. For that we need to do the Thevenin's equivalent circuit of this one. So I have my VTH, this is my RTH, VDD is 10 volt, this is my RC, okay. So my IB, therefore my IB will be given by this VTH minus BBE on, which is 0.7 by RTH. Okay, so and we know that RTH is equal to RB1 parallel RB2. Okay, so if I calculate this parallel between this RB1 and RB2, I will get a value of 13.88 kilo ohms, and of course the VTH, as we have seen previously, is given by VDD into RB2 by RB1 plus RB2, and this comes out to be 0.7464. Okay, so if I now estimate this IB, what I'll get is 0.746 minus 0.7, and RTH is 13.88 kilo ohms. Of course, these steps would come after evaluating this one. Okay, so implies my IB, if I estimate this value, it is coming out to be around 3.33 microampere. So this is the IB at which I will be operating. Okay, so my IC will be equal to beta times IB, and this comes out to be around almost 1 milliampere, 0.98 milliampere. Okay, and the other operating point which is sometimes asked is this VCE voltage. Okay, or basically the DC value of this V out. Okay, so this is also sometimes asked, or the VCE DC voltage or the V out is equal to, we know that it is VDD minus IDRC. If we estimate it, it is around 10 minus, this is 0.98 milliampere into 3 kilo ohms. So this happens to be approximately 7 volt. Okay, so why this is asked is because we want to make sure that the transistor is not going into the saturation region. So the midpoint of this is important. So where the DC, so the DC value of this point is important. We will discuss about this one more in the next class. Okay. Okay. So now let's do the small signal analysis and find out the gain. So for small signal model, I have my V in, and of course I have my RS. So now we know that this RB1 and RB2 will be in parallel, as discussed before. And I have my model of BJT here. This is R pi, and the emitter is grounded. And I have here my current dependent current source, IC equal to beta times IB. And I have my RC here, and this is V out. So I'm supposed to find out the ratio of V out by V in for this. Okay, so let's work step by step and try to find it out. Okay, so note that here I have I'll be developing this voltage VBE. Okay, and the current IB will be passing through this. Okay, so to find out this current IB, what I can do is first I can find out this voltage VBE, and VBE by R pi will give me this current IB. So let me write down. So my VBE voltage, right, based on a simple voltage division. So you see here now R pi and RB1, RB2 parallel will become in parallel. So this resistance, which is RB1 parallel RB2, will come in parallel with R pi. Okay. So basically, if you see here, the current flowing through this whole network is V in by RS plus R pi parallel RB1 parallel RB2, and of course this is the current flowing through this whole thing, and if I multiply with this RB1 parallel RB2 parallel R pi, I will get the voltage VBE. Okay. So this is my BBE, okay, and I can find out my current IV now. Therefore, my current IV is equal to BBE by R pi, and I can get the BBE from here. On the other side, if you see this IC, as we have done previously, right, my V out will be equal to minus small IC RC is equal to minus beta IB RC. So now I can substitute this IB from here, which is minus beta BBE by R pi RC. And now I can substitute this one from this equation. So let's call it as equation number 1. This as equation number 2. So this one is from 2. And if I substitute the BBE from 1, what I'll get is minus beta RC R pi. I'm just bringing these 3 terms this side, and I can substitute BBE with this one, okay. So I have my R pi parallel RB1 parallel RB2, okay, and V in, of course, and this one. So this is RS plus R pi parallel RB1 parallel RB2. So in this kind of problem, what you are supposed to do is just proceed step by step, and you will see that one parameter is dependent on other, and we just need to keep substituting it, okay. So we just need to remove the intermediate parameters. So the intermediate parameters you can see here is the small IB, small BBE. So finally we have to find out the ratio of the V out by V in with respect to all the resistance, beta, and this R pi, okay. So therefore my gain AV is equal to V out by V in is equal to minus beta RC R pi . Okay, so I have just brought this V in this side, so then I have got this ratio V out by V in. So now let's try to estimate all these parameters, okay. So if you find out the beta is, in this case was, beta in my case was 295, and RC is 3 kilo ohms, okay, and R pi, we can find out this R pi, so let's calculate here, right. R pi is equal to Vt by IV, which is basically Vt in room temperature is 26 millivolt. Please try to remember this number. Room temperature is 26 millivolt, and IV is, we know that it is 3.3 microampere, okay. This is equal to 7.87 kilo ohms, okay. So this is my R pi, okay. Okay, my R pi is 7.87 kilo ohms, okay, and then of course I can and in my case RB1 parallel RB2 happens to be 13.88, and if I make this one parallel with 7.87 R pi, this whole expression I'll get a value of approximately around 5 kilo ohms. RS, we know that it is 2 kilo ohms plus 5 kilo ohms. So if I estimate this whole thing, what I will get here is minus 80. So this is approximately minus 80. Minus 80 is the gain of this amplifier. So if you observe here in the expression of the gain, so this RS has come in the denominator, okay. If the value of the RS is quite high, then you can see that the gain decreases, okay. Whereas if the RS is very small compared to this, then if it is negligible, like if it is in few ohms, right, so we can see that it will not affect the gain. The other thing is this R pi, if you see here, is comparable with RB1 parallel RB2. Okay, RPI is 7.87 kilo ohms, which is comparable to this RB1 parallel RB2, which is 13.88 kilo ohms. The reason is because my IB is very small, significant. So if you see here, if my RPI is, if my IB is large, then this term may be very small compared to RB1 parallel RB2. So in that case, we may approximate this whole thing with RPI, but in this case, they are comparable, so we cannot do that. Okay. Okay, so with this, we'll end our discussion on the introduction to the CE amplifier or the common emitter amplifier. In the next lecture, we will try to see more in details of this amplifier. Thank you.